Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Integration of non-uniformly spaced discrete functions. Integration of non-uniformly spaced discrete functions can be somewhat tricky because the datasets are not uniformly spaced, making it more difficult to directly apply the methods such as trapezoidal and Simpsons rules that are formulated for uniformly spaced discrete datasets. In cases where the integrand is known explicitly, the analyst has the freedom to choose the numerical method or number of panels, etc. In such cases, uniformly spaced discrete datasets are generated to simplify the computation procedure and reduce the CPU time. Non-uniformly spaced discrete functions are generally derived from random data sampling or experimental observation. In these situations, the analyst has no choice but to use the available data as is. Consider a non-uniformly spaced discrete function on the interval from a to b, whose abscissas are given as follows, for which the interval sizes vary. The area of the trapezoid bounded by the panel on xi-1 to xi is written as follows. For the whole data range, we obtain a general formula for the trapezoidal rule as follows. To obtain a formulation equivalent to the Simpsons rule, a second-degree Lagrange interpolating polynomial passing through 3 data points is obtained as integrating this quadratic approximation from xi-1 to xi+1, corresponding to the area bounded by the two panels, results in the following expression. Employing this result to a dataset of even number of panels yields the following, which is the composite rule equivalent to Simpson's 1/3 rule for non-uniform discrete functions. For an odd number of panels, the integration of the quadratic interpolating polynomial over the last panel is obtained as follows. In the case of an odd number of panels, apply the equivalent Simpson's 1/3 rule to all panels, which should be even, except the last panel, and apply the above formula to the last panel. The advantages of the integration methods for non-uniformly spaced datasets are: such formulations allow estimation of the numerical integrals of non-uniformly spaced datasets derived from random data sampling or experimental observation. Numerical integration procedures based on open or closed Newton-Cotes formulas can be easily employed for non-uniformly spaced discrete functions. The disadvantages of the integration methods for non-uniformly spaced datasets are: estimating the error and its bounds is not an easy task. The order of accuracy is dominated by the largest h-values. CPU time increases due to computing the coefficients, depending on the data interval sizes. Let us consider the experimentally gathered dataset tabulated below. We will use the trapezoidal and Simpsons rules to estimate the given two integrals. We tabulate the given dataset and adopt subscript notation from 0 to 6. The interval spacings are evaluated and assigned subscripts starting from 1. The area of a single trapezoid is found from the following expression. After evaluating the areas of the trapezoids, we tabulate the results in the 5th column. The sum of the areas of the trapezoids gives the estimate for the integral, which is 286.25. When we integrate up to x equals 4.5, all we need to do is calculate the area of the trapezoid for the last panel, which is found to be 529. We can add this result to the estimated numerical integral from 0 to 3.5, which yield 815.25. Next, we will estimate the integrals using Simpson's rule. The number of panels from 0 to 3.5 in the dataset is even. Hence, we can use the following approximation for a pair of panels. We will label the area from x equals 1 to x equals 2 as A1. The area from x equals 2 to x equals 2.6 is A3, and from x equals 2.6 to x equals 3.5 is A5, whose computed results are presented in the table. Summing up all three areas, we obtain the estimate for the integral to be 280.97 and recurring 6. The number of panels from 0 to 4.5 is odd. We have just calculated an estimate for the integral from 0 to 3.5. Right now, all we need to do is to calculate the area corresponding to the last panel or interval. We note that h7 equals 1 and h6 equals 0.5. The function values of f5, f6, and f7 are 209, 336, and 722, respectively. Applying the single panel approximation to the last panel, we get 514 point recurring 3. Recall the integral from 0 to 3.5 was 280.97 recurring 6. Adding up these two quantities, we obtain the estimate to be 795.31. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.